Okay, I think we should slowly get started here, and we'll have people trickling in probably in the next few minutes. But let's get started right about on time. So welcome to the second day of the workshop, and we will start with our keynote speaker, who is Bill Harris today. So Bill is an associate professor of physics at MIT. He's trained as a particle physicist, so he received his PhD from MIT in 2011, so right before the Higgs boson discovery. Then he went to CERN, and he was actually part of the discovery work on his discovery at CERN as a CERN fellow, after which he became CERN staff as a staff scientist. So he has various interests both in physics, but also in machine learning. So in physics, he's interested in things such as dark matter searches, measuring properties of the Higgs boson, and jet substructure. And then on the machine learning side, he's both interested in kind of new data analysis methods enabled by AI and machine learning, but then also kind of the hardware side of things, of how to kind of accelerate things such that we can run these algorithms on huge amounts of data, which we have these days. So he's involved in various organizations around both of those topics, and has played a key role, for example, in the FastML organization on the hardware side, and then on the data analysis side, you can actually see the logos here, IFI Institute and the A3B3 Institute, where he plays a leadership role in both of those. So today we will hear about his most recent work on machine learning and AI for physics. So the title is Automating Particle and Astrophysics Research with AI. So let's take it away.
All right, thanks. Yeah, so I'll start this talk at the Higgs discovery, which you may remember, right? So fun time. You can ask me. I think I'm somewhere here. Maybe I'm not in this photo. Anyway, but I was sitting around here. So if you next to Valentina, who's a faculty here, right? So if you want to ask questions, I can show you a photo later. But I want to start here with the actual discovery plots. And so the interesting thing that you'll see is that on the left you have Atlas, right? So we had this like 5 sigma excess, right? The right you have CMS, you have almost 5 sigma excess. But the part I'm interested in is this dashed line, right? So, and if you look, this is the expected sensitivity, right? So Atlas was sensitive at about 4.5 sigma. CMS was sensitive at 6 sigma. And so Atlas, CMS, was very sensitive, and another experiment got lucky, right? And this difference, people didn't talk about at the time, but you can go back and ask, like, what was the difference? And you can point to kind of a few key things, and most of them were actually machine learning related. So CMS had more sensitivity in the kind of Higgs to gamma analysis. And that was, largely because of machine learning. And actually, CMS had other channels, and like the most sensitive with Higgs to WW. And that was actually because of a machine learning based kind of tagger that we were able to do to remove pileup. So there are a bunch of little subtleties. And at the time, there were hints that, maybe machine learning was going to kind of change and accelerate things. And, I think we all saw this in the mid-2010s when software frameworks, GPUs, and all of this stuff became readily available. It kind of changed the dynamic for how we can do things, right? And now, they're kind of everywhere. So this talk, I'm going to go through how AI has changed HAPS. I'll look through a bunch of kind of examples, and then I'll talk a little bit as well about Astro, about gravitational waves in particular. And I want you to kind of get excited about some of the interesting things, capabilities. And I'm going to touch on like a lot of projects, try to show a high level vision. But there's lots of stories behind all these projects. So feel free to ask questions, right? But the kind of key message I want to get to everybody is things are changing so fast that I think it's actually becoming more accessible to everyone. AI is now, I think, more accessible than it ever has been to people. All right, so here's CERN, here's LHC. I guess you guys all know how these things go. Here's just show you, what do? We collide protons or other things on target. You get a spray of particles. It's very complicated. And then, it gives you a point cloud, or some people call it a point cloud, but it's a little more complicated than that. And so you have this, and the whole challenge is trying to infer what process this is, right? And so you can stare at this thing and try to look at this. And like any good particle physicist would look at this and know immediately that this is a dijet event. And one of these is very likely a gluon, and the other is very likely a quark, right? And you can, know this like quickly. Here's an example of something that looks like that. This is a kind of fun dye jet, and you can look at this and say, oh, this is a normal jet, has with one prong. This is a jet that has kind of two large energy deposits. So this is maybe from a resonance. You can then zoom in here and actually notice that these kind of two prongs are actually from displaced kind of objects, particles that live for a long time. So if you zoom in at this vertex, you'll see that. And then you realize, oh, this is from two B quarks. And so this is very likely and then you can compute the energy of these, and it turns out it's very likely to be a Higgs boson, right? And so the kind of dream of an LHC physicist is to go from these collisions, like I said there, and be able to analyze the details, and then come up with a vector, right, that gives you the probability of what this process is, right? Is this a Higgs, right? In this case, this one's a Higgs to B quarks. Let's say 60% likelihood. There's maybe a 20% chance that it's a dijet, maybe 10%, something else like Z to B quarks, and maybe there's 5% chance like something new and mysterious that I don't understand. And this is kind of the goal of particle physics, right? If I were to summarize like what we would want to do is to actually come up with a vector that we know with the utmost confidence, what our event is, right? And the dream is that every collision you do, right, you immediately get this vector. And we collide 40 million collisions a second, and it's actually not 40 million collisions of protons, it's 40 million collisions of 60 protons at a time, right? And so you're looking at 60 collisions at the same time, and ideally you want a vector for all of them, right? And the idea is once you can go from this, right, you can then immediately start to map this out to fundamental constants, right? So here's a plot of like the Higgs coupling to vector bosons and to fermions, and ultimately we can look at the rates of all our different processes. And then you can reduce this to a bunch of, kind of fundamental constants about the universe, right? And this tells you about how the Higgs kind of gives matter to the universe. And ultimately, right, it can tell you about other things. So if you study like two Higgses, like is done here, you can actually measure the stability of the universe, right? And lots of other things. So the dream is really to do this in as little steps as possible, and really come up with a kind of confident measurement of what we're doing, right? And so this is always the thing that we have like kind of lying in the background of how we're going to solve, or how we're going to do particle physics problems, right? Can we translate direct things? So to kind of do this, I want to go back to a 5th grade science textbook, right? And I want to kind of illustrate this thought process using the kind of science paradigm that you would have learned when you were like 10 years old, which is the scientific method, right? So, you do an observation, you ask a question, you make a hypothesis, you perform an experiment, you make a conclusion, right? So this is the easier one to read, but this is the one that I think's in that textbook, right? So let's go and do the scientific method. And so this is how I'm going to phrase it. I'm going to kind of observe, so take some data, or if I'm an astrophysicist, like observe with a telescope, ask a question, right? I think, I don't know, I like Higgs bosons. I think there's something wrong with the Higgs boson. And then, you take your data and you want to, reduce your data. So get some data that is Higgs boson-like, right? So you do some sort of selection, you reduce the number of variables, and then ultimately you formulate a hypothesis, right? A hypothesis. Maybe I see too many high energy Higgs bosons than I expect, right? And then you build a reference, you perform a hypothesis test, and you get conclusions, right? And so I'm going to go through the scientific method in this talk, but I'm going to start from the conclusions and go backwards and show how we can automate these things, right? And how AI can kind of interface at all the different levels, right? So how do we do a hypothesis test and get to a conclusion, some sort of p-value? Well, the way we do this is typically in kind of two schemes. A scheme where we know what we're hypothesizing, right? So we know what the kind of the hypothesis is, and we're looking for some specific signal, right? So say we're looking for a Higgs boson, or we're looking for something else. And this is what the kind of classic way we do LHC searches, right? Arguably, right, you could reduce every single search to like taking some simulation, right? Predicting taking some data, training a supervised learning algorithm, and then, fitting the discriminator. And broadly speaking, that's like 95% of LHC analyses. There's way more complications in how we actually, if we actually train a neural network, you don't necessarily do that. How do you model a simulation? There's a gazillion questions we can ask. But ultimately, we're just trying to test something. Like, do we see new physics here, right? How do we, what's the rate of Higgs bosons in this region? And we take our simulation and we try to match it to the data, right? The other thing you can do is anomaly detection, right? So which you say, well, I give up on making a hypothesis, right, of what the signal might be or what the process I'm measuring, and I'm just going to look for anomalies, right? And so there, what you would do is you just look at your data set and you try to find overdensities. You have to inject some sort of inductive bias, right? So you need some sort of idea of what you want to assume. So in this case, right, my eyes will tell me, oh, I see an excess of events. I'm secretly assuming that my events cluster right in this variable here, which is turns out to be the mass of 4 leptons, and this is the Higgs boson, right? Okay, so in this context, we can start to ask, well, how do we do this in the modern world? And the other data point I want to inject is that we're in a world now where things like fitting can become way more complicated. So here's a fit that one of my students is doing. It's a 2,500 parameter fit, right? So this is a kind of unfolding of a physics process. And so they're basically, every bin in this histogram is being kind of floated, right, in the fit. And then in fact, there's like, every one of these, there's like 5 of these, and you fit all of them simultaneously. And this we can do now in PyTorch with in a few seconds, right, on a GPU, right? So the point being is that, with kind of GPU and modern computational libraries, you can do kind of fitting that like was insane before. I mean, I remember when we did the Higgs discovery, we had a 2,500 parameter fit, like 2,500 nuisances, and we would, press enter, and then we'd have to wait 24 hours to get the result. And, half the time there was a bug, and then you kind of would go nuts, right? And not sleep and freak out. And then, management would say, we need these results next week. And anyway, I can tell you more about that at coffee. So given that, right, and given that, our fitting frameworks, now we can write in auto-differentiable languages like PyTorch or JAX, right, we can actually do kind of fun things. So one thing that we've been doing recently is just taking our normal fits that we do at the LHC, our bump hunts, and actually trying to make them differentiable. And so we asked the question, well, we like to fit discriminators. We also like to fit bumps and mass. And we said, well, do we want coffee or do we want tea? And the answer we decided was yes, right? And so the nice thing is that if you have differentiable fitting, you can actually train a discriminator and fit simultaneously. And what you do here is you actually make your likelihood differentiable, right? And then you can actually simultaneously train a discriminator with a differentiable likelihood. So how do we do this in practice? Well, we actually learn a likelihood. And typically what we'll do is we'll train this on simulation, right? So we train a discriminator, and then we split our output of our discriminator into categories, right? We could do this into like 2 or even more. And like a simple way of doing this, but there's certainly more complicated ways, is to just to define a weight, right? Which is the score. The score is bounded between 0 and 1, and one category can be score times the variable you want, and the other category can be 1 minus score. This histogram you can make differentiable, and then you can define a differentiable likelihood and simultaneously train your neural net and fit with a full fit with nuisances, right, back propagating to the discriminator. And so what does this get you? This gets you the ability to not only to train a neural network, but to actually train this on data with a full complicated fit model that allows you to kind of extract your signals, right? And so this is something we recently did. We call it Doppio, mostly because we use this for 2 categories. And my postdoc who, like, I wanted to call it split and fit, but he likes coffee, and he won the naming fight. And so how does this work in practice? Well, here's a actually example from CMS Open data. So this is fitting a W boson resonance in a jet. And this is before. So if we train a neural network on about 20 features, we get this nice bump here, right? And we look at the data, and this is our fit. But now what we do is we then fine tune our fit on the data, right? And if we fine tune on the data, we can actually increase our signal, right? Increase our significance and actually improve our fitting. Why are we doing this? Well, our simulation is not perfect. This allows us to adjust, right, to the imperfect aspects of the simulation, profiling nuisances, profiling uncertainties in our fit, making it possible to actually get better measurements, right? So this allows us to simultaneously train a neural network and fit. A way of viewing this, you can imagine, is that one axis you have a discriminator, right, where you have your signal on one side and your background on the other. On the other axis, you have a variable, right, you're fitting. Now, of course, right, you don't need to do this just in 2 variables. You can do this in many variables. But suffice it to say, right, it's easy to visualize. And so we've done this in a few cases. I just showed you CMS Open data. We did a case in kind of future LHC running where we mocked up kind of a incorrect simulation for di-Higgs production. And we were able to go from the kind of incorrect simulation gave us 2 sigma sensitivity to something like 3 sigma sensitivity, where the ideal significance is like roughly 3.2. We're able to kind of recover the kind of mismodeling of our Monte Carlo just by profiling in the data, right? And so there's lots of questions you can ask, but that's a kind of recent thing. So what is this doing? It's just allowing us to kind of embed, deep learning into training. And naturally, you can go a step further and ask, well, what if I do anomaly detection? And so you could actually make a loss function where you just look for a bump, right? The bump could be anywhere in your distribution, and you try to split your categories to one that's bumpy and one that's not, and simultaneously fit these and actually extract a signal. And so you can actually extend this very generically to kind of a broad range of signals. So this is a simple way of anomaly detection, but we can try to generalize this bump concept a little more. And the idea then it would be to just actually look for overdensities without some sort of, in this case, we're splitting and fitting, right, without actually some kind of fundamental fit, but just to look for some overdensity compared to some reference. So if I look at this data, right, I see an excess of events, right? And my eyes are telling me there's an excess because I have this prior that there's some sort of cluster of events in this data, right? Well, we can inject it, we can embed this prior into a neural net and actually try to fit for this excess, right? And so this is actually work from Gaia Grostov, who's a postdoc in my group. And she has a strategy to basically, given some reference, right, look for an overdensity, right, under the inductive bias, right, that our overdensities are smooth Gaussian objects. And so what she does is she fits a bunch of Gaussians, right, to the data. And so you can see, you can, get the kind of deviation from your reference, right? So she fits the Gaussians to the deviations from the reference. So the blue is our reference distribution, right? And you can look for overdensities this way. And so you can define an anomaly score, which is just basically, how large is your local deviation with respect to your reference, right? So the big win for this is that, well, this works in one dimension, right? We've been able to fit Gaussians, look for bumps this way, right? And if we can even, if we want to fit the background and control it, we can do it this way as well. But if you start making this inductive bias of a Gaussian, it's actually very powerful in high dimensions, right? So I can imagine now asking the same question of, well, how do I look for an overdensity in 2D? Well, you can imagine, building a reference distribution, right? And then looking for some cluster of events on top of it, right? And you don't need a strong prior, right, for your reference, as long as you know how to control your reference. And then you can look for some cluster just by injecting the prior of looking for some Gaussian or looking for a collection of Gaussians. And this scales quite nicely to 3D, where your clusters become even more visible, or to 1000D, where the clusters become even more visible. And if you're just fitting a bunch of, like a Gaussian, a 1000-dimensional Gaussian, you only have, well, in this case, 1000 mean parameters and 1000 width parameters, right, assuming the kind of covariance of the Gaussian is diagonal. So you're talking about a neural network here that only has, order 2000 parameters. So it's not a large neural network, right? And so you can actually take a very high dimensional data set and actually look in these high dimensions for some single overdensity and try to find the most likely overdensity. And this is a way to do anomaly detection. Gaia's developed kind of the full formal approach for this, right? This is an approach we call Sparker. And this works, she doesn't fit just one Gaussian, you can fit kind of, an ensemble of Gaussians, so something like 5 or 10, and actually look for multiple overdensities at the same time. But the nice thing is that this scales very nicely to high dimensions. So we've been able to kind of go up to 1000 dimensions, just looking for clusters, right, of axes of events, compared to some reference distribution. And so where is this useful? You can imagine, right, in 2D, you have an axis on top of some reference, right? So this works there. you can also look for a small excess, right? That's kind of right in the top, right? So, this algorithm works here. When your excess starts to become kind of out of distribution, you find that simpler metrics, things like, out of distribution, metrics, something like MMD, right? Things that are kind of like far apart where there's just not a lot of data, right? These start to suddenly become, more useful. But certainly, if you're trying to find some excess in, on top of data like an overdensity on top of some large background, this is a kind of approach, like fitting a kind of n-dimensional Gaussian on top of your data is like a good approach. And so, just to show you, we've tested this fit procedure now on kind of lots of different data sets, right? So here are kind of physics data sets where we do kind of gravitational waves, and we do the Higgs boson. And actually, we find, so our sparse kernels, we have a version that's like, sparse kernels, so it's only a few Gaussians. And then we have another one where we just spawn a lot of Gaussians, right, like order 1,000, but the means don't move, right? And you just float the amplitudes, right? And that's, effectively the kind of overdensity algorithm is the same, but the flexibility is not as good, right? So it doesn't have this nice Gaussian inductive bias in the same way that we have with just a few Gaussians. And so what we see is that, well, for kind of physics cases, right, both approaches, outperform like a rule or kind of a metric-based approach like MMD. But when you go to kind of sparse data sets, right, and things that are very high dimensional, very complex, right, so like trying to look at outputs of an LLM, right? So in this case, we're trying to find fake lines of a LLM generated version of the Divine Comedy, right? You can see that these sparse approaches like way outperform. And what it is they're small networks, right? They're only a few thousand free parameters, right? And they're looking for overdensities in this very high dimensional space. So you win by the dimensionality because you're just looking for a kind of a sparse, like you're looking in a sparse space. And then you win by the fact that this is a kind of easily trainable model, right? So it's kind of a new architecture that's very good for overdensity. All right, so what have I shown you so far? I've shown you a way to kind of inject AI to fitting and a way to use AI to kind of build, look for anomalies, like look for strange overdensities. So that kind of tells you approaches that you can do kind of once you have your data, right? But how do we actually formulate the hypothesis, right? So formulating the hypothesis, typically what we do, we need some data, we need some simulation or some reference, and we try to do some hypothesis, right? How do I compare A versus B, right? You make a null, you have a null hypothesis, and you try to look for something, right? So the question we always ask when we do this is, when we make our hypothesis, is how well do we trust B, and how do we kind of model this? And this is where kind of I think all the physics happens. And this is the part I'm always very excited about. And how do we do this? Well, the kind of traditional way to do this is we take our data. Our data can be very complex. So if you're talking about collider data, you can have as many as thousands of particles, right? And each particle gives you a 4-vector, and usually features associated to that 4-vector. So you're talking about data sets, right? A single collision can have 10,000 features, right? And then what we do is we take our physics knowledge, usually, we featureize it, and then we try to use these features to construct our hypothesis, right? And ultimately, our concern here is how do we compress this down to things that we understand and we're confident. And so I view this as the Plato stage, right? Where we take our data and we kind of mold it into something. We try to make Plato homes and Plato dogs and things that we, right? So this is kind of the way I think about my research, right? And the nice thing now is kind of in the old days, we would featureize by hand, right, using physics knowledge. But now we can use ML to featureize. So we can go to, just like I went to, Nano Banana and I asked, make me an image of a collision turning into a Plato dog, right? We can actually ask the same features now. And this is where I think there's lots of exciting things to do. So to give you a very simple example of where this really started to work, let me show you what we did for the Higgs discovery. So in 2012, we wrote a bunch of high-level features. These are physics-based observables. I'm not going to explain what they are. There's something called R9, which describes how an electron looks, right, compared to a photon. There are other variables like the energy of the energy, like the centrality of the energy, right, in a crystal. And we can write down order 20 variables. And what we did in 2012 for the Higgs discovery is we use these to make a neural net regression to predict the actual true energy of our particles. So in this case, we make a nice electron peak, and we actually correct the electron energies based on all these shower shape variables, right? And this was a big kind of improvement in our sensitivity. Well, 10 years later, we said, well, we don't care about these features anymore. Let's just take raw hits, embed them in some neural network. In this case, we did a graph neural network. And then let's just train for the energy. So now what are we doing? We're just giving our neural net just the raw information, and we're giving it the task at hand. And we're saying, you figure out the features, you solve the problem for us. And it took us 10 years to do this. But finally, we were able to outperform kind of these simpler algorithms. So this BDT is a high-level feature regression, and this is the resolution you get, right? And so we were finally able to get better resolution from raw information. But this took 10 years. And this is basically the advent of having like powerful machine learning to kind of actually automate your procedure to diffusionalize. But now that we have this, right, we can then go ask the question of what other things can we featureize? How much can we really explore in physics? And so this is how I view hypothesis testing now, right? At the LHC is we have some simulation, we have some data, we featureize it, we then take our hypothesis test. And our goal here is to minimize the impact of the uncertainties, right, when we featureize. And when we can't minimize it, find a way to embed the uncertainties into our featurization so that they're expressed, right? So we do some reduction. And so I'm going to show you a bunch of different ways to do this, right? Now let me illustrate this. First, by letting your AI actually try to understand how we do this. So I have two images, right? The right image is Van Gogh. The left image is a Dr. Van Gogh. And if you look carefully, you'll see a few small differences, right? So I'll let you look for a sec while I finish my coffee. All right, now if you look, you probably see some things, right? And you'll notice that there's a star here, it's not here. If you're really good, you'll notice there's like a door open here. It's not here. I think that's right. Now let me ask you another question, right? So I just showed you Van Gogh for like 20 seconds. Which one of these paintings is Van Gogh, right? Yeah, right. So in this case, right, it's the top right, right? The rest of these are great, Impressionist artists like Monet and Renoir and I think Manet, right? But the point is that the top right has the same kind of, brush strokes, features, style of art that we saw in the previous painting. So what did I just do? I forced you to learn about Van Gogh, even though you might not have wanted to. And I then told your brain was able to extrapolate to lots of different, paintings, right, that are different, right? And it's this extrapolation process is the way I actually view featurization, right? In the old days, right, 5-10 years ago, before we were using kind of these fancy ML, right, we would ask the question to an AI and say, how would you find the difference between these two paintings? And the way we would do this with the AI is basically take the left painting, take the right painting, overlap them, and subtract and find the difference. This doesn't tell you anything about the features in the painting, right? It just tells you where the difference is. You get a nice, clean difference. And you're learning things, lining them up pixel by pixel, but you're not actually learning anything about how painters paint, right? You're just learning how to find the difference, right? And this paradigm, this difference in paradigm kind of is fundamental to how we actually can featureize and how we can actually use AI to kind of build our hypothesis test. So let me give you a few examples. So first I'll talk about the quack algorithm. So this is developed with one of my students, Sangyan, former students. And the idea here was to come up with a distribution that gave us a probability of a specific process. So you can imagine a process where you measure your background. And you can train, for example, a normalizing flow or an autoencoder or something. And you get a metric that tells you on one side, this is high probability that it's, your background is here. So high probability that this is background. And low probability on another side, in this case, the right side, that it's background. Now I can take another process, right? I'll call this signal, right? And my background is going to be low probability signal. my signal is going to be high probability signal, right? So it'll live down in the bottom. But my signal is also going to be low probability background. So if I have a signal, right, it's going to be a low probability background, high probability signal. Background is going to be in the opposite diagonal, right? Low probability of signal, high probability background. Now you can construct a space, right? So this is a 2D space. And off this kind of diagonal, you have things that are neither signal nor background, right? And so what does this mean? Well, if you want to have it the inductive bias that you're looking for some signal, right? It doesn't necessarily need to be your hypothetical signal. It could be another signal. Well, you can start to look in this space that's signal-like, not background-like, to actually look for your new signal. And that kind of underlines, the construction of this space underlines the whole process to do anomaly detection, right? So let's look at this in action. So what we can do is search in the kind of bottom right for new physics. And so what I want to do is just illustrate this by taking a data set. They're just going to be sad and happy cats. They're going to be rainbow colored, right? Just to kind of add some features. And this is my data set, right? There's a hidden message there, and you'll see some happy cats, some sad cats. And so if I go ahead and train this neural network, and this is an actual neural network, I can get a space like this, and we can look at the space. And what we'll see is on the bottom right, we get our signals. On the top left, we get our background. And then we'll see along this diagonal, we get all the kind of strange anomalous things, right? So things that don't fit signal and background. And so what we can do is we can exploit this full two-dimensional space and actually search for anomalies, right? And so this is a way of featurizing that knows about signals and backgrounds, but then actually isolates all of the data in specific regions. And this allows us to kind of look for featurization. We can add our ability to look for high-dimensional overdensities to this space. And this gives us an ability to actually look not just for the signals of the backgrounds, but to look for the things that are unexpected, right? And just to show you that this works, we actually, when I was doing this is analysis I did with Oz. And when we were actually trying to validate this, it worked. We had a control region where we didn't expect any signal. And we saw this huge signal here. And we freaked out, and we didn't sleep for about 2 weeks because like there really should not have been signal. Like the laws of physics told us that like there shouldn't have been a signal here. And it turns out that for reasons that I still don't understand, there were so many selections and cuts that if you had a top quark background just in this region of data, it would manufacture a bump. And we were able to kind of demonstrate this very clearly. But the nice thing is that our algorithm picked this up without telling us, right? So it told us there was a net overdensity. It told us there was like anomalous excess. And we just kind of got this just by looking at our space. So it does work. There's lots of other kind of anomaly detection algorithms that work. But what we find is that this one, right? I don't think I have the plot. I think Oz will show the plot in his talk. But what we find is that when you know actually roughly what the signal is like, the quack algorithm tends to outperform the other algorithms. But if you don't know what the signal is like, the other algorithms, have less kind of, priors about what the signal will be like, and they perform better. So now I want to kind of extend this idea a little more, and I want to take an image, and I'm going to augment this image, right? And so I'm just going to take an image, augment this, and then I want to build a space, kind of the same way I did with quack. And so I'm going to take another image and I'm going to augment it, right? So in this case, I took a cat, I gave it glasses. I took a dog, I gave it glasses. And in my space, I want to kind of spread around my data. So I want to make sure the data is kind of spread around, make sure the RMS of the data set is large. But I also want to make sure that my cats live with my cats and my dogs live with my dogs. So I try to minimize the distance in my embedded space of my cats with my cats and my dogs with my dogs. And I try to spread everything around, right? So I try to maximize the distance over the whole data set, right? So what happens if I do this? Well, I start to get some order, right? So in this case, in a two-dimensional space, I'll notice that my cats will all live in one spot, my dogs will all live in another spot, and my augmented dog, right? They're kind of by construction going to be close to each other, but my dogs that are not augmented will also be close to the dogs, right? So I'm telling my latent space, just like I told your eyes when you looked at Van Gogh, to build some sort of order into your data set, right? So this is another way of building space, like quack, where we can actually start to look for physics, right? And I'm going to take my same cat data set, and I'm going to give it shift symmetry. So I'm going to shift my cats around in my space, right? And I'm going to tell my neural net that this shift symmetry, our space should be invariant to this. So if my cat and my shifted cat, they should be embedded in a new latent space where this shift symmetry doesn't matter, right? So they shouldn't be in, like, I'm going to minimize the distance between my cat and shifted cat. So I'm going to go and do this. If you know anything from physics, this is equivalent. Shift symmetry is from Nether's theorem, equivalent to saying, conservation momentum, right? So things that shifted are equivalent to conservation momentum. This is another way of actually making this neural network. So there's like a broad range of colors here. It's another way of saying we want to make this neural network colorblind, right? Adding the shift symmetry. So let's go ahead and train the neural network. Okay. It's training. This is our new embedded space. It has these fun features. And what you'll notice is that our background kind of live up here, right? Our signals, right, live in this tail, right, over here. And now you see that all the anomalies kind of live out in an uncontrolled part of the space. And so what I've been doing is I just featureized my data. I built an embedded space. It learned how to classify things. And it built this latent space. I never told this network what a cat with smiley faces, or a cat with a sad face is, or a cat with crazy colored eyes and ears is. I just told it to shift everything in X and Y, and that this embedded space should capture, right, all of the, should try to capture all the physics we care about, right? So then I can go ahead and use this space, right, to actually map this onto physics. I can take the same idea with the Higgs boson or with quarks and gluons, right? And in this case, my shift symmetry instead is I'll take a simulation and just run it many times. And so these kind of quarks and gluons, the way we simulate them is you start with a high energy quark or gluon, you shower, and then this shower is a kind of every time you shower, right, can be a different shower, different number of particles. Yes?
Quick clarification question. When you shift X and Y, are you shifting covariates and labels, or is it coordinates of the image?
It's just the coordinates, right? So yeah, I'm not changing the labels. Yeah. So I can take my shower, I can take my object, I can reshower it many times, right? So the same quark and gluon will give me a different shower of many different particles. I can reshower this many times, and I can take my object, and my reshowered object should live in the same part of the space, right? So I keep my initial process constant, and then I vary my reshowered object. This is another way of saying, right, we're trying to embed like a wave function, right, and not collapse the wave function in the embedded space. It's like some notion of quantum mechanics, right, into embedded space. So I take my object, I augment it, and I say, try to minimize the distance. And so I end up with a space like this. So here's a Higgs, right? The cyan is the original, the red is the augmented. Here's a quark, right? So these are just particles, with the size of the particles is the energy, right? And I say, let's build an embedded space. So I do this into 8 dimensions. I get a space like this, right? The red's the Higgs, the blue is our background. And then I can project this down to 1 dimension, right? Or 2 dimensions, right? And you see that the Higgses live on one side of the space. The quarks and the gluons live on another. And in fact, the quarks and the gluons are separated as well. You can see at least the blue and the orange are clustered by eye. And what have I done? I've just made a mapping. I never told it what a Higgs boson was. I never told it what a quark or gluon was. But I just told it that we have this process that, these objects can lead to showers of many different particles, and that these showers should be in the same part of the space. So what does it learn? It's learned how to separate Higgses from quarks and gluons. So this is a kind of generic process that allows you to build an embedded space that allows you to kind of structure and featureize so that you can perform, your hypothesis tests. You can search for anomalies, or you can actually do, supervised learning. In this case, right, since we were varying our shower around actually our uncertainties, you can imagine varying all your different systematic uncertainties, so varying the different uncertainties in your simulation. This is what you would get for a normal variable, like this. These are the uncertainty bands, like just the ratio of the shifted uncertainty to not. But in this case, since we're trying to vary the uncertainties and embed them in the same point of the space, we end up that our embedded space is invariant to these uncertainties, right? So what are we doing? We're projecting away the uncertainties in our simulation, right? And you can see that in this case, right, by forcing the kind of object and its object, reshowered object, where I've changed the uncertainties in the model, I've actually been able to project them more, right? And so this is a way of actually reducing the impact of systematic modeling, as well as a way of featureizing, right? And so you can search for, new things. So what do we learn from this? Well, if I were to kind of use this task and then do a normal kind of Higgs or W boson classification, in domain I get a gain, right? Because I've pre-trained it with this kind of showering task. And if I were to pre-train it with a Higgs versus a background and then apply it to a W, so then I take a W boson and I fine tune it, I can actually get a 10% gain on top of, let's say, state-of-the-art classification. So what does this mean? It means also I can train on all of my objects, all in one big training, build an embedded space, and actually use this embedded space to do all the physics measurements and hypothesis tests that I would ever want to do, right? And so here's an example of an embedded space for the LHC. So this is with 5 different processes. The purple here is the Higgs boson. We did not train on it. It learned to featureize it, right, on its own. And in this case, what we're doing is we're taking this is originally a 1,000-dimensional space. We projected it down to 4 dimensions, and it's captured the physics we care about. And so once you have these 4 dimensions, right, you can start to do all the kind of fun anomaly detection searches, fit for resonances, do things using these various variables. Just to show you how generic this is, right, here's an equivalent version with gravitational waves. So these are 8 different processes of black hole mergers, black hole Bremsstrahlung, kinks, glitches, blah, blah, blah. And then the supernova-like objects, we call them white bursts, right? White noise bursts. Those we didn't train on, and you can see, again, we've been able to isolate them. And if you try to actually do an anomaly detection algorithm for LIGO, you would typically want to look for white noise bursts because we actually have no idea how to model these guys, right? We just know that they're going to be different and have, broadly speaking, a few set of features, right? So once you have this space, you can then start to do fun things. You can start to do things like anomaly detection and so on. Now, I want to keep on this theme of embedding space and show you one other way to embed space, which is to use optimal transport. So you can take an object. So for example, we have a collection of particles, right? And then what I want to do is I take my collection of particles and, this is cases of 48-dimensional space. It's like a collection of, I think, 16 particles. And we want to embed this into a 2D space, right? So what I'll do is I'll build a transformer that takes this object, reduces it to 2 numbers. And then what I'll do is in this space, I'll force the difference between my 2 complex objects in the 48-dimensional space in the embedded space to have a distance. And in this case, we're going to use EMD, which is just a Wasserstein, an optimal transport distance, the Wasserstein 1 distance between these 2 objects. And what we can do then is you train on like 1 million jets, or at least 3, you can start to build an embedded space. So you can compute all the pairwise optimal transport distances between these. And then you can embed this in a 2-dimensional space just by forcing the distances between all of these objects to build the space. Now for 3 objects, right, you can get a 2D space, right? But if you train this on 1 million and you force it to be 2D, you start to kind of build an embedded space. And this space actually captures the physics you care about. Now, in this case, we use this optimal transport metric that was developed by my friends at MIT that has lots of nice physics properties, right? So it's an approximate energy distance between these 2 objects. And once you have this space, you can actually, you're effectively featureizing your space. You can start to do lots of, searches, look for new physics, hypothesis tests, and so on. Another fun thing is that we don't necessarily need to use a Euclidean geometry, right? We like to look at Euclidean, but for objects like jets or things that have tree structures, like evolution of plants and stuff, a better way to embed this is often a hyperbolic geometry. And so you can imagine embedding this in a hyperbolic space as well. All right, so now I'll just show you a bunch of things that we can do with these things. So this is the embedded space where we used optimal transport. And what we see is that in our 2D embedded space, we start to see order in how we actually classify things. So in this case, our objects have prongs of like different number of quarks in the object and mass. And we can see that mass approximately corresponds to one axis and pronginess, it corresponds to another. If we were to try to use like kind of other embeddings, so things like t-SNE, we find that there's kind of disorder. There's no notion of mass and pronginess, right? If we were to use things like UMAP, which is another kind of like low dimensional embedding, you find that mass and pronginess are kind of not well defined. And so by using these kind of optimal transport or using metrics that are physically motivated, we can build these embedded space that actually capture the physics we care about, right? You can imagine doing this to quantify things like anomaly detection. So we can actually, look at this embedded space, compute the area, right, like the convex hull of the embedded space that our selection captures. So you imagine let's say you train an autoencoder or you train a supervised algorithm, you have a discriminator. You can cut on your discriminator and then look at where this lives in the embedded space. And you can make an area adjusted ROC curve. And typically when we do supervised learning, right, and we compare this to anomaly detection, we see that supervised learning is more sensitive. So this is like a normal ROC curve you would see for signal versus background when you train a supervised learning algorithm with a specific signal. And we see that the blue, is more sensitive than like an anomaly detection algorithm that's just looking for deviations from the background. But if we compute an area adjusted ROC curve, so we look at the actual area that the different algorithms explore, we find that something where you don't have a signal prior, right? So actually can span a much larger amount of parameter space, right? Compared to the actual kind of MLP, so to supervised learning. So what we're doing here is we're making a kind of quantifying how anomalous our algorithms are by looking at how much of the embedded space they can separate signal from background. Right? So this is just like one thing. So what have we done, right? We've, in the old days, we would talk to a theorist. We'd take our data, talk to a theorist, we'd get some features, right? And then we go do all our measurements. And this is what we did, let's say 10 years ago. And now we're in an era where we can talk to our theorists, get all our physics principles, right? And then have the neural net automate the featurization for us, right? And this allows us to kind of do things like anomaly detection and all sorts of other things. And just to show you kind of very concrete example, here's an approach where we fit our Gaussians for anomalies. We just look for anomalous signals. And this would be what we would get if we had a 57-dimensional kind of raw space, right? This is full optimizations of everything. We're trying to separate the green from the blue. This is our test statistic. And if we were to then just use our physics principles, build a 4-dimensional space and do the same search, we suddenly can separate green from purple, right, very significantly. So you see very clearly this is the case where we have an injected signal. And so you can go from like 1 sigma deviations to like many sigma, right? And so what are we doing? We're featurizing, we're data reducing, we're getting rid of the things that don't matter through the knowledge of physics. Another thing we can do is we can actually embed uncertainties in this. And so this is a recent study we're doing where we actually, in the process of building this embedded space, we actually give it in the loss function a term that linearizes our uncertainties. So this is varying a nuisance parameter, right, in our simulation. This is the kind of variation you would get at different parts of the space. And so you can see if you don't do this, if you just make a learned space, the variation can be positive and negative, right, as you vary the nuisance. So it makes it very hard to actually get give very concrete analysis if you're trying to kind of do a search or measurement on this space. But we can actually embed a loss term that linearizes our nuisances. And so you can go from something that's kind of disordered to something that's ordered. So you can actually profile nuisances in this embedded space. And here's just a kind of validation that this works, right? And we can actually do like an SBI in our embedded space where we profile over our nuisances, right? So it's the recent study. So what does this mean now? Well, we have a scheme where we can just give raw data, we can featurize it, and then we can just dump this into like a fit or some anomaly detection algorithm and all do this in one automated step, right? And so we have a pipeline to do this. And just to show you that this works, we took some Higgs data, some raw inputs. In this case, we took like 4 vectors from Higgs to form muon event. We gave it our physics guiding principles. And we said, why don't you just automatically discover the Higgs boson for us? And this is what we get. The algorithm, right, we just gave it a collection of 20 variables. It didn't know what mass is, right? Mass is like the fundamental variable for particle physics. We always just look for bumps in mass. It did not know what this is, right? And we said, give us the most anomalous events. So it gave us an anomaly score on the output. We didn't give it what the signal was. We just said, look for overdensities, right, in the 4D space. And the most anomalous events ended up being these events. which end up being clustered in mass, which end up being the Higgs boson, right? And in fact, we're almost as sensitive as a supervised algorithm, right, to discover the Higgs. So we can actually automate the whole procedure of discovery. So what have we done? Well, we've taken this whole process of hypothesizing, looking at the data, reducing it, hypothesizing it, and performing our hypothesis test. We've automated into one thing. And so this is what we call AutoSciDAC, which is a scheme to kind of featurize and then automatically search for something. And you can do this in the case of anomaly detection, but if you know what your signal is, you can also do a fully supervised version of this, right? And if you don't know how to model everything, right, you need to do some fitting to model your backgrounds, you can imagine doing this with a differentiable fit where you can actually backpropagate through the featurization as well, right? So this is a kind of automated toolkit. So this is a way to automate most things. But then what about these guys over here? The actual kind of data reduction, and this is differentiable. What about this part? Well, this would require, at this point, LLMs or some agents. So if you don't know what to do to kind of reduce your data, you need some sort of robot. And so I figure, I'm running a little behind time, but I'll talk about, I figure you guys all know about AI slop. I figure you guys all hate it, but I feel like at some point we have to embrace it. And so let me just talk about slopping until we drop. So now we want to make the whole thing automated. We want to run our experiment. We want to feed our data, perform our hypothesis, do anomaly detection, do supervise, do all our measurements. The last step is you need something to orchestrate all of this, right? And AI agents have emerged as a tool to do this. And so we asked the question about, I guess, 6 weeks ago, how much could we automate this? And we just figured, how much could we push this to the limit? And so out of this, we wrote a paper. And we had a very provocative title. AI agents can already autonomously perform experimental high energy physics. Just to do this, right, there's 20 pages of human or mostly human written text. And then there's another 520 pages of auto-generated full analysis, right? And you can go online and read these. And what did we see? Well, we built a workflow where we gave it a kind of a concrete task. We said, here's the data, here's the problem you want to do. And then we fed it into an agent. And then we had review agents that would feed back to that agent, right? And then they would talk to each other, back and forth, argue. And then after a few hours, they would spit out results, right? Just to show you the kind of equivalent version of this, like at the LHC, you start with some legacy code, it doesn't work, you have to build a little framework, then you show your office mates, and they say, oh no, this is garbage, and you go back and forth. And then finally, like you kind of update your code, and you finally say, oh, I'm ready to present this. So now you go to the subgroup, and the subgroup has a bunch of people who ask you to do a bunch of silly things and also to improve your analysis. They usually find a few mistakes. They also find a few things that waste your time. And then you need to update your framework again. And then after like a few, 2 or 3 iterations of this, right, you finally get to go to a convener, right? And then the convener will say, oh, are we ready to publish this or not? And then they usually are not happy with it. And so there's another set of feedback. And then finally you go for what we call pre-approval. And then you give a talk, and then you go through another review committee. And then finally, once it passes that review committee, you can make a preliminary result. But then if you want to make a publication, you then have to go through kind of the review from senior management, the collaboration. You have to go through a so-called collaboration-wide review. And then you have to go through a final reading where a bunch of 70-year-olds read your paper and argue about the English, right? And then finally, you get to actually submit this to a journal for publication. This whole process takes, 1 to 2 years, right? It's a long, arduous process. And well, you still need humans here, right? At least before you were, if you wanted collaboration approval. But a lot of these things can be automated, right? And the feedback we see from these agents is kind of comparable to the feedback we see here, right? And just to show you what we did, here's just a query. So this is the full query for analysis, right? This is end to end what we saw. scaffold a run measurement of this blah, blah, blah variable, right, in this process with this data. We used old data from the 90s because we wanted to start with something simple. We did use one LHC data set, but we wanted to start with something simple. And we asked it to produce this variable, which didn't exist in the 90s, right? This is a variable. There's no paper on this from this data set. It has been studied at the LHC. And we give it some details of how to do it and what to compare. And out of that, it just spits out a result, right? So this is the result it gave, right? This is the result that we saw from a recent collaboration. You can compare them. They're qualitatively similar. Some of the features are actually quite similar. And suffice it to say that, right, it's actually producing things that are getting close to publication quality, right? And this is something novel, right? Nobody's done this, right? So, and the kind of features, the deviations from our model make sense, right? It's not something, it's something I would have done, or say one of my students would have done, right, in the data set. This took, right, you feed it this query, we didn't touch it, and then you get an answer about 3 to 4 hours later, right? So that's kind of the scale of how these things work. There's a lot of details for how we actually do this. Right? There are ways that you need to kind of train the agent to actually do your job correctly. So actually, one big thing we realize is you have to let it explore. So you give it the data and say, look at all the features, look at the simulation, look at the data, make a lot of plots and explore and think about this, right? And then read these papers. So we give it like a database of papers. And then once it's done with the kind of exploration and strategizing, it actually kind of writes the code for the analysis. And then once we have the analysis code, we can then go and look at the data. And so we tell it to partially unblind, look at 10% of the data, go to human, and then show all the results. And if the human says, this looks good, then you finally get our result. And so that's basically the flow. All of this is public. All of this is just a bunch of text files. By the way, we just feed the agent these text files, and it can do all the analysis on its own this way. Just to show you a smattering of other things that we've done, these are just all results that we did. This was 2 days of work, right, in Claude. So it's the ability to kind of produce significant results very fast. The other thing to notice is that things are getting better kind of every week, right? This is not going from Sonnet to Mythos. This is using 2 versions of Claude models, right? Just going from 4.6 to 4.7, which is a kind of incremental update. And you can see, right, just by eye, like this plot looks a lot nicer than this one, right? And you can actually look at the details of the analysis, and they actually are better. So, and just to show you, right, how good is it getting, right? Here's analysis I did when I was a postdoc, the Higgs tau tau in CMS. So I did this number, so I know all the problems with it. We had the agent do this for one of the channels. There's like kind of 3 major channels. And if I compare this result with the kind of CMS sensitivity, it's getting there, right? It's not the full sensitivity. So full sensitivity it's like 40% better. But if I compare this with the other experiment, like the crappy one, we're able to get about the same uncertainty for the same process, right? So it's doing things that are pretty good. All right. And yeah, you can look at it like, this is overall our results. You can compare consistencies, and it's getting there, but it's definitely not all the way there. So what does this mean? It means that we have a tool now that can kind of allow us to do bigger and bolder research. We now have a way to kind of framework that streamlines our result. It's a way to kind of really automate the whole procedure. We still have a lot of work to actually kind of validate that this is doing a good job, right? We need to do more things like compare this with standard measurements, right? We need to make fake data sets, that show that we can actually recover the things that we care about. But ultimately, I'm excited that this will kind of build a new path where students don't need to be, code monkeys, and they work more like professors, where they talk to their agent, the agent writes the code, gives it feedback, they go back and forth, and they kind of can produce results and do much bigger, bolder, kind of more exciting things. Yeah. All right, so this is what I call Super Dario world. Right? Dario Amodei is a friend of mine, so I think I'm allowed. And I know for a fact he likes Super Mario because I talk to him about this all the time. All right, I was going to talk about gravitational waves, but I think I don't have time. But suffice it to say, we can do the same paradigm there. And let me just highlight the the part you probably care about is why is this such an interesting problem? Well, we need data rejection, background rejection at the order of 10 to the minus 7. And this tail of the background, right? What makes it so interesting is that this tail is not Markovian, it's not IID. This is all glitchy data. So this is a glitch, right, from 2 detectors that are aligned, right? And you need to come up with a strategy to model these glitchy data, this non-Markovian data. It's rough, right? And this makes it really challenging. And so that's the hard part of gravitational waves. Our solution was to brute force it, and we figured out how to automatically generate, take existing data and, clone it a gazillion times through so-called time sliding, right, of the different detectors, and then injecting as many signals as we possibly can. And then we get to things that can do gravitational wave detection. And just to show you, this is what the problem looks like. We have our data, and then if we see a gravitational wave, we flag it as a signal. So, and you can do things like, right, SBI, right, looking where this is in the sky. And there's lots of kind of fun tricks you can do there. So I won't talk about this. But suffice it to say, the reason we do this is we want to do this really fast. So we want to do this really fast. So the old tools would take like minutes, right, or hours to run on tens of thousands of CPUs. Our stuff takes like, fractions of a second to run on 1 GPU. And in fact, we're running, if you're interested, we are running this kind of full SBI pipeline, detecting the data, making alerts. We're running this online. It's been running publicly for almost the last year, right? And just to show you, we're like substantially faster than what was before. So here was like our first alert. It took us 24 seconds. And this is with a lot of most of it is shuffling data around. It was like 1 second of actual compute. And then the kind of conventional approach, which is compute limited, took something like 10 times more time. And so this is just to give you an example. All right. So in summary, I'll just skip to the end. The scientific method, right, can be automated, right, and AIs can make that tool. So all right. Thank you. So.